you're probably asking why I showed you that. That is a highly informative video made in the 1910s to show the development of today's topic, the new-ish British sub, the Astute class. Currently there are 5 of them, technically 6 if you count the one that's not in service. It is quite intriguing. So then, let's start. Welcome to the whole chapter, the most entertaining part of the video. So then, I have a question for you. How do you dive hundreds of meters underwater? The answer is a hull specially designed to resist the extreme pressures at that depth. So how do you do that, I hear you ask? It's actually quite simple. All you need to do is make a sphere. Although there's a problem, a sphere doesn't have enough volume to store the things you need, like missiles, crew, nuclear reactor, engines, Boris Johnson, really anything else. So, if you take a sphere and extrude it, you make a cylinder. Now then, you have something that looks like a sub, and can still survive the pressures at that depth. The hull in the Astute is made from steel and has an inner pressure vessel and an outer free-flow space, to allow for objects that don't mind being wetted under pressure to sit outside the inner hull. The inner hull is split into 3 sections from front to back: operational living space, where the crew lives and does most of their work; the reactor compartment, where the reactor and most of its systems are held; and the machinery space, where most of the propulsion and power generation machinery are. Although not directly part of the hull, the conning tower and sensors mounted on the top are quite important, and technically part of the hull, so I couldn't not mention it here. The entire exterior of the sub is coated in acoustic tiles, which absorbs sound from both outside and inside the sub, making it a lot harder for an enemy sub or potentially a torpedo to detect it, and even if they are using an active sonar. The hull is also fitted with 3 sets of degaussing coils, which are large magnetic coils that stop the sub from emitting a magnetic field that can be picked up by aircraft and other subs. This is needed as the sub's hull acts as a large magnet. To finish the degaussing process, the sub needs to pass through a large magnetic sizing facility, which are these large arch-like structures that use a magnetic field to negate the magnetic field present actually in the sub's hull by providing a magnetic field that opposes the one. We are currently in front of the place where they assemble them. So then, how do you assemble a nuclear sub? They're quite large and some components that they use are quite fragile. The answer is to use a modular system. The Astute is made up of 2 sets of 8 units. One set is for the outer hull, the other one is for the interior. The hull set would be forged and transported to the hull behind me, where they would be welded together using these mechanical welders that run along tracks around the circumference of the inside of the hull. Apparently they reduce the welding time by around 40%. It is important to get this right, as only a slight deviation from perfection can reduce the crush depth of the hull by a substantial amount. Most of the interior is mounted on modules, which most are specialised into a specific role. They are pushed into the hull by hydraulic rams, where they can be fully finished and connected to the sub. This includes the MPMP, or main propulsion machinery package, which consists of the turbine, gearbox, generator and propulsion machinery. It was tested at the Smite facility, which had its own oil burners to make steam to drive the system. Fun fact: while they tested it, they used it to produce power for the grid, making it a small power plant. Also, there is the FIRM, or Forward Engine Room Module, which is a 3-deck high module that contains a multitude of systems, including air conditioning, ventilation, heating, air purification, water treatment, and of course the engines. Due to all the system of the FIRM, it is quite cramped, and benefits from being assembled off-site. The next specialised module is the MRM, or the Manoeuvring Room Module, that contains the control console, switchboards and other components for monitoring reactor and power systems. When this module was installed, it was only half done, as there was a lot of cabling, 17 kilometers to be specific, that needed to be installed into the module and the sub. The final module is the CDM, or the Command Deck Module, which contains the combat system, including the combat deck, antenna and other systems. This module benefited particularly from the modular construction, as it could be assembled and tested off-site, so any problems could be fixed quickly, so I found to mess around inside the cramped compartments of the sub. This was the final module to be installed. Now we can close the outer hull and prepare it for its first dip in the ocean. Now the sub will be wheeled out on a platform to the ship lift, where it can be lowered into the ocean. Now the trials can start. Most of these were done on land before it entered the water, and the systems tested with it moored. But, of course, they need to figure out if it could be a sub. So, dive trials it is. They would dive the sub to about 15 metres below the surface and use 16 tons of lead fed out over 4 trolleys to figure out the sub's characteristics. They also perform weapons trials, where they use dud torpedoes and tomahawks to test if they could use the weapon systems. Then the reactor was fueled and tested by starting off and shooting the power up, test if the reactor performs in the way it was predicted by the scientists. Most subs use reactors as their primary propulsion. Why is this, you ask? Well then, watch this chapter to find out. The basics of any reactor is to use spicy rocks to heat water and turn a turbine, in this case to propel the sub. In actuality, the spiciness of the rocks comes from fission, which is the splitting of atoms using a neutron. This process happens all the time, as nuclear fuels naturally emit neutrons. All a reactor does is optimise the process, allowing for a chain reaction. But if we just left it like this will quickly get out of hand, so we use control rods, which are rods made out of a neutron-absorbing material that slow down the reaction and allow for you to set the output of the reactor. Although bare fuel is not good at absorbing neutrons, so we need to help it a bit. In this case we use a moderator, usually water but not always, to slow the neutrons down and allow for more to interrupt the fuel. Also, water is not good at the high temperatures that a reactor operates. At that sort of temperature it will evaporate. To stop this from happening, they use a pressure vessel to keep the water liquid by keeping it under pressure. The reactor used on the astute is a PWR-2 reactor made by Rolls-Royce, based on a Westinghouse PWR. It uses weapons-grade uranium from around 93 to 97% enrichment, which allows for the reactor to be quite small compared to its output. It is shielded by a mix of lead and borated polyethylene blocks. Because of how deep the sub operates, the amount of radiation inside the sub is even below background levels. This is because the seawater naturally absorbs the radiation. After it was assembled, it was tested in the Vulcan facility, where it's hooked up to a system that emulates what you would find inside the sub to make sure that it works and matches the specifications. So now we have a source of heat. How do we turn that into motion? Starting from the reactor, cooling water is pulled out of the reactor and fed into a steam generator, which, if you couldn't have guessed from the name, uses superheated water from the reactor to heat up a secondary line and generate steam. Now the steam moves to one of the two turbines, where it spins them, and either generates power or rotates the gearbox and by extension the propulsor. Now it moves on to the condenser, where it's cooled by seawater, and condenses back into water and fed back into the steam generator. So if you're like me, you're probably asking why they don't just heat the steam back up and feed it back through again, cutting out the condenser. Simply, if there's no condenser there's not a big enough pressure difference to drive the steam around, meaning that you'll just be pumping steam around the power plant, turning your power plant into a power consumer. Although not directly related to the propulsion system, the reactor can also be throttled to allow for a variable amount of steam to be produced, and by extension change how fast the turbines spin. The Astute uses a pre-swirled ducted propulsor. The difference between a typical propeller and this is that this uses a cowl to contain the blades and allow for the same propulsion with a smaller diameter. Due to the cowl's construction, it traps most of the noise inside the propulsor, making it quite quiet. Although what you do if the propulsion system breaks in some way, which is bound to happen in combat, there is an electric motor that can operate the propulsor if the steam brace system doesn't work. But what if that breaks? There's a small propulsion motor that's hidden in the hull that can be deployed with 4 hydraulic jacks that allows for the sub to move even if the main propulsor is destroyed. Now it can move, but how do we go underwater? That's where the hydroplanes and the ballast come in. Starting with the hydroplanes, they're the fins that you see on subs. They are hydraulically actuated and allow for the sub to descend underwater and to more fly in the ballast system, although they do require forward motion to be used. Now for the ballast system, the sub has 6 ballast tanks, 4 main tanks and 2 trim tanks. When diving, the main tanks are filled to create close neutral buoyancy, and the trim tanks are used to fine-tune it. They can also be filled to allow the sub to dive. To get water out of it, they push pressurised air into the ballast tank from gas bottles located nearby. They can also be refilled underwater by the use of 2 compressors. So, how do you survive hundreds of metres underwater for an extended period? We've already partially discussed one of the systems required: electricity. Most of the sub's electricity is generated by the turbo generator, which is connected to one of the 2 turbines. The sub's grid is split into 2 parts, an AC and a DC part. The AC part is where the generator is and most of the equipment is, as well as including a connection that can be hooked up to an external power source. To connect them, use a static converter. The DC part contains the batteries for storing excess power, and both the secondary propulsor and the motor are in this part. So what if the reactor fails again? Switch to battery power. The batteries used in the Astute are a bit weird. They use some lead acid batteries instead of the more modern lithium-ion. Why is this? Well, they're much cheaper and do not leak as much electricity over time. And they're a larger weight, so they can be used to save less, and they are also more reliable than the others. The system also includes 2 diesel generators, an AC one and a DC one, for powering the sub when the reactor is down. These generators are 8V396 generator sets made by MTU. They can be operated at the surface or at a shallow depth using the snorkel. Now for the air system. Of course underwater you need a constant supply of air or you'll quickly suffocate. So now all that electricity we were making, we're going to need it. It all starts with an electrolyzer that breaks up hydrogen and oxygen using electricity. The oxygen is obviously put into the subs there, while the hydrogen is sent to one or two destinations that we'll discuss in a few seconds. Now there'll be CO2 in the air. How do we remove it? The answer is to use a monomethylalanine packed tower carbon dioxide scrubber. Use monomethylalanine, also known as MEA, if you couldn't have guessed, to remove CO2 from the air. I'll be referring to it as MEA for the rest of the section as I can't be bothered to say its full name. At the start of the scrubber, the air enters the packed tower and passes through a tank of MEA. The CO2 is absorbed into it, and the MEA is captured and pumped into a stripper, where the MEA is heated to about 120 degrees C, where it releases the CO2, allowing for it to be captured. Then the MEA is cooled back down and put back into the packed tower, allowing for the whole process to repeat. The next piece in this puzzle is the carbon monoxide and hydrogen eliminator that removes these pesky gases. The carbon dioxide is extremely toxic, and hydrogen is flammable, so remove them as a priority. They do this by oxidizing them into water and CO2, by heating them up to 315 degrees and forcing them from a catalyst at high speeds. Well, the catalyst can be poisoned by moisture, so it has to be kept at above 150 degrees to prevent water from falling on the catalyst. The final thing is a gas management plant that combines the hydrogen with the CO2 to create an aqueous solution that can be either stored or dumped overboard depending on what they want to do. Now for the final part, the system is triad. Water. So how do you get clean non-salty water while underwater? Use a reverse osmosis purification plant. How it works is actually quite simple. It takes the seawater and forces it through a semi-permeable membrane, leaving the salt on the other side. Now we have water. It's stored in 4 separate tanks and used for things like the showers, toilets, taps, and the sprinkler system in the weapons bay. Due to the size of it, it can store enough water to supply the sub continuously for about 7 days. Although not directly related to what we talked about, most of the things in the sub are on these X mounts that stop the noise emitted from them from being transferred into the hull and by extension outside. FBI, open up! Where you can see things. Let's start with the masts. All the masts are mounted on the conning tower and are behind doors. Starting at the front, you have a platform where you can use the most powerful optic imaginable, the Eyeball Mark 1. Behind that you have the navigation mast, which is used for a flag and the wind direction indicator. Behind that you'll find 2 electro-optical periscopes. Unlike normal periscopes, they do not directly allow the crew to see outside. Instead they have 2 cameras, visual and IR1, that allow for the crew to see outside. Because of this, they can pop up and quickly rotate and retract to decrease the chance of detection. The image can then be analysed by the crew to identify the threats. Behind these masts you'll find the communications and navigation mast. These contain 3 antennas that allow the sub to communicate with the GPS network as well as other frequencies. Next you have the SATCOM communication mast, which allows for the sub to communicate with the Skynet system. Behind that there's a radar and electronic support mast that contains the antenna for listening in on radio and radar signals. It can also be used to transmit data. Behind that you'll find the snorkel and the exhaust of the engines. An interesting fact, they added a system into it to stop water from entering the snorkel by closing it when water is detected and reopening it when there's none obviously in there. Although not technically related to what we just talked about, the sub is equipped with an INS system, which allows the sub to find its position on the water with no external input, which by measuring the acceleration and using it to find out the speed and then the distance. The one the astute is a fibre optic gyro compass, uses a laser fed through a fibre optic cable to measure the acceleration. Now we are underwater, how do we find out what else is also under there? The answer is sonar. The astute has 4 sets: the bow array, the flank array, the towed line array, and the intercept array. Starting with the bow array, it uses a large amount of hydrogens and transducers to detect targets. They usually don't use the transducers, but they can be used to ping targets to provide a more accurate distance and profile of them. It's set aside a dome that when filled with seawater becomes transparent to sound. Next, the flank arrays, which are put along the side of the boat and can be used to either locate enemy targets, and they usually their range, using its large size. Apparently it's the largest array ever equipped to a sub. Now for the towed array, it's a sonar array that was deployed out the back of the sub, and is usually more accurate than the ones mounted on the sub. It is sent more than 600 metres behind the sub, and hydrogens are contained in the middle of 2 vibration isolator modules that stop the sound from the sub or the drone from being picked up by it. Finally, the intercept array is mounted in front of the conning tower and used to detect a wide range of targets, including ships, subs, sonars, sonar buoys, and torpedoes. So now we can see things. How do we interpret that and use it? The answer is a combat management system. It takes the data from the sonar and mass and allows it to to be used by the crew to assess the situation and use the weapon system. It is made up of 7 consoles that are attached to a server. The consoles do not process any information, they just provide graphics and allow the crew to interact with the system. Allowing for a more redundant system, as there's one break, you can just go to the next one. There is an ape console that's used for special intelligence functions that is in the Electronic Warfare Office. It's run by 3 servers, 2 central servers and 1 support server. The support server takes input from the sensors and communications and processes them. The information from the support server is then assessed by the crew to figure out what they want to do. If they choose violence, they can send a signal down the tactical weapon system highway to the SWIM, or submarine weapon interface manager that controls the torpedo system. Also, just a little fact, the system has a printer for some reason. I don't exactly know how to read one, but it is there. The entire system uses a bespoke OS called ACMS that is apparently based on a really old OS used by the Royal Navy. Before they used Windows, probably to save money, but they had a large amount of problems given the fact that Microsoft could just examine the systems and be fine. But generally, it was more generally inefficient and, well, much easier to hack. This decision also allowed them to hook up the sonar quite easily, as they both use quite similar software and hardware. All this computing power is stored in modular cabinets that allow for any component to be swapped or removed and can easily be reconstructed if there's a different geometry that's needed in the future. It's also water cooled by pumping the hot air from the cabinet into a heat exchanger. Now for the part you've all been waiting for, the actual weapons. So let's start with the WHLS, or the Weapons Handling and Launch System, which has the loading and unloading weapons as well as launching them. It stores 32 weapons on 2 3-level racks on either side of the sub. To load and unload weapons, they're sent on a rail into the hull that enters into the racks. To do this, they also connect a temporary rail and a walkway to allow for the weapons to enter the sub more easily. To load a torpedo, they open the breech door and push the weapon into it. Then they connect devices such as the guidance wires, and then the muzzle doors are opened. They pump in more air from the water transfer tank to force the weapon out. The system can also modify the amount of force it puts out depending on the weapon. The first of all weapons is the Spearfish torpedo. It is a large heavyweight torpedo that started service in 2001. It has a large enough warhead to blow through most subs and ships. It can use both passive and active sonar, but usually uses passive. Although when it is active, it can be quite deadly, as it can filter out decoys and other torpedoes and focus just on the beam it emits. It also allows them to fire salvos of them. It uses a gas turbine engine to power it, which is apparently quite quiet. If you didn't know, gas turbine engine is basically just a jet engine, but instead of using the exhaust to propel it, it runs it through a turbine and either makes electricity out of it or turns it into rotational force and uses it to propel something. Next on the list is the Tomahawk Land Attack Missile, sometimes known as the TLAM. Specifically, it's the Block 4 version. This is made in the US, if you didn't know. It's launched out of the same torpedo to use the Spearfish and uses a solid rocket mode to fire itself out of the water. It can be used for a wide range of tasks, including recon and, of course, destruction of enemy assets from a long range. It can be directed by the sub by using a pre-programmed flight path that can even include alternative routes and targets. Or it can be directed by satellite, allowing for more direct control of it. And last on this is the Special Forces Bay. Although not technically a weapon, it houses some of those powerful weapons Britain has, the Special Forces. The Astute has a number of features that allow for more effective operations, such as kayaks, inflatable boats, and it also includes the SFPB, or the Special Forces Payload Bay, that's suspected to contain a small sub for use by the Special Forces. So that was my first long-ish scripted video. I hope you like it. Like and sub if you want. Now then, it is time for me to return to the void.